Hi everyone, I am Suhaib Mujahid and I will be presenting our work about using others' tests to identify break-in updates. Updating the dependency is an important practice. So, when you are moving from an old version to a newer version, you are expecting new features, fixing bugs, or patching security vulnerabilities. However, this still has some risk. Dependency update could induce a breakage. The breakage could be intentional, like changes to the API itself, or unintentional, like bugs. Developers tend to mitigate this issue by using semantic versioning and restricting the update to a specific major version that respect the backward compatibility. Also, running regression tests in the local environment or in the CI pipeline can help to detect and catch any unexpected behavior. However, in practice, bugs still can find their way. Breakage-inducing updates, it's a problem because semantic versioning could be wrongly used by the developer of the package themselves. Also, regression tests could miss a newly induced breakage. In this work, we are focusing on the dependency between packages in NPM ecosystem as our use case. NPM is a package manager for the JavaScript and it has more than 1,300,000 packages. And these packages got downloaded in last month only more than 83 billion times. Packages in NPM are part of a big dependency graph, and dependencies between packages are very common. In our approach, we want to take advantage of the dependency graph to improve the test coverage and the test quality when we update our dependency to a newer version. When you are using a package on NPM, you are not the only user of that package. Other packages and projects could use the same dependency and even the same version. The main idea in our approach to leverage the test from open source projects and packages to increase the possibility of catching breakage-inducing versions. When there is a new version in very high level, our approach depends on run the test based on the old version, then run the same tests again based on the new version. If the tests pass based on the old version and also pass again on the new version, then this indicates that the package is free of a breakage behavior. However, if the test pass on the old version and fail on the new version, this indicates that the package could induce a breakage behavior. Finally, if the package fail on the old version, we ignore it because such failure it will not be related to the new version. Many stakeholders can get benefit from this approach. For example, the developer of the package itself can know if the new version is breaking their clients. Also, the user of the package can make more educated decision when they decide to update their dependency. So they can decide if they want to update carefully to the new version or wait for the next version when it patch the breakage behavior. Also, tools like bots that automate the dependency update can take benefit from this approach before opening a new pull request to ask for updating the dependency. Now we want to validate our approach. We need real-world cases of a breakage-inducing version to serve as our ground truth. To do so, we start by mining more than 290,000 GitHub repository of JavaScript projects. From that projects, we extracted more than 478,000 dependency changes. These dependency changes include more than 456,000 dependency upgrades and more than 21,000 dependency downgrades. Here we are interested in dependency downgrade since developers tend to downgrade when they have an issue after updating to a newer version. To eliminate false positive, we ignore changes that combined with changes other than dependency downgrade. Also, we manually examine the commit message of commits that perform the dependency downgrade, and we select only cases where the commit message confirms that the downgrade is because of a breakage-inducing version. Based on that, we end up having 10 cases of breakage-inducing versions. To run our experiments, we build the required environment. We start by replicating the NPM registry, then we create what we call it time machine proxy that allow us to simulate the NPM registry at a specific point of time as needed. Also, we build a framework to run the test and record the result on each stage. Since the dependency graph is complex and big, and not all packages in NPM have tests, and running the test for all packages is inefficient, we start by identifying the most suitable package to be used. Since packages on NPM are shipped without the tests, we need to retrieve these tests from their Git repository. So we filter out packages that do not have a valid Git repository. Also, we eliminate immature and dummy packages, and we kept only packages that depend on the target versions. Next, we prioritize the dependent packages to be used for the testings. We use for that the test coverage and the NPMs rank. The NPMs rank is a rank used by the official NPM search engines. This rank depends on the many metrics related to the quality, the maintenance, and the popularity. After running the experiments, we want to answer our research questions. The first research question is, can we improve the test coverage using the tests from the dependent packages? The second research question is, can we detect breakage-inducing versions using the tests from dependent packages? For the first research question, we trace the execution of the test in our experiment and we calculate the test coverage for the target packages. In this figure, we can see in the x-axis the number of dependent projects that we run, and in the y-axis we can see the cumulative test coverage that we achieve. We can see that based on the experiment that we run, we were able to achieve up to 55% of test coverage by considering only the test of dependent packages. It's worth mentioning that this test is simulating the real use of the package API. To examine if the test from the dependent projects cover parts that are not covered by the project itself, we combined the test from the dependent package with the test from the package itself. As a result of this combination, we can see that we were able to achieve up to approximately 80% of test coverage. For example, in the Express package, we were able to increase the test coverage from 22 to 60, almost 60%. For the second research question, as I mentioned before, our approach depends mainly on running the tests based on the old version and then running the same tests again based on the new version. Based on our experiments, we find that 34% of the builds pass on both of the old and the new version. Also, 4% of the build pass on the old version and fail on the new version, which indicates a breakage behavior. Finally, we find that 62% of the builds fail on the old version. Based on these numbers, we were able to catch 60% of the breakage updates. In conclusion, based on our experiments, we find that tests from dependent packages were able to improve the test coverage of the package by including real-world tests that simulate the real-world usage of the package. Also, our approach were able to catch 60% of the breakage-inducing versions. To wrap up, I started by motivating our work of using other tests to identify break-in updates. Then I explained our approach in very high level. Next, I showed our results related to improve the test coverage. Finally, I showed that our approach were able to catch 60% of the breakage-inducing versions. Thank you for listening and have a good day.